I will actually preface what I'm going to be saying to you guys now in this section on GDS is there's a lot of text. There are a few equations. I'm not going to read them word for word. Really, it's more about having you be able to use this as a compendium, as a resource in the slides when they're provided to all of you to look up later and kind of flesh out what we were talking about and connect it into some of the more formal representations. So what I want to do is kind of just provide an overview as to why it is we want to move from what we were seeing before about systems defined as interfaces or as boundaries with particular views and say, all right, well, now if we really want to get into this and understand these systems, understand how they change, understand what might be construed as best, well, we need a way in which we can formalize those properties that we later on want to keep, those things that we want to verify, those things that we wish the implementation, whether it's an implementation to test these properties or an implementation that is ultimately the software version of what it is you're trying to describe, we would like those properties then to be something we can carry forward with some form of faith. And so what we're going to be providing here now in this section is
Let me
one
answer
particular
that
way
question.
in which this is done.
There's
Sorry?
a question in the chat.
Thanks.
Just a note. So GDS is about describing the mathematical objects and their properties. So if you have other tools that are related to like the verification of the implementation, we may eventually have to construct some mappings between those mathematical languages. But our GDS is actually derived from the formalisms that are used in control theory, which is my background. And in particular, what we do is interpret the crypto economics sort of token engineering kind of design problems as economic microcontrol. And what I mean when I say economic microcontrol is that we're actually asserting invariance. And so we built mathematical generalization of the tools that are used for defining and asserting invariance in control theory and translated them for defining and asserting invariance in a more economic context. And so I will say that there's probably some to be done work to build the translators to other languages that are used, but I'm relatively confident that this is not a huge leap, because what we're presenting is actually very, very general, meaning it can represent an arbitrary state machine, but it has some things that are borrowed from control theory that are not necessarily the focus in some of the other modeling languages. And I think Jamsheed's going to be speaking to this. It really boils down to the difference between describing things in terms of what will happen and what can happen, and being very anal about the notion of admissibility, the notion of in a way, it's a kind of generalization of strong typing of the inputs, but in a slightly different way. And so I would invite people to you know, as we kind of go through this, think about and even in the future contribute to the mappings, because we aren't being very opinionated about the implementation part. We're simply saying we're using the tools that we need to best represent, to design, even not just represent, design the mathematical objects that we wish to have implemented, because they have the properties we need to generate the system level results we need. And that's why a lot of our design work is, you know, literally this tool has been this GDS has been work Jamsheed and I have been doing for several years in a wide range of design problems. And it's not obvious to people because it's part of our design process. And once we have a mathematical representation, it can get translated into whatever form or whatever language is needed by the downstream implementers, or downstream verifiers for that matter, right? Because we're talking in terms of validation. We really care about trying to make sure that we've got the right mathematical object to solve the problem, and then we have to work with somebody else to make sure that that mathematical object is implemented and verifiably, right? Does that make sense? We'll jump back into it, but I do want to make sure that this doesn't seem like it's errant random stuff.
Yeah, and it's also not a formal language. Secret knowledge. I don't know if it's secret knowledge.
We're trying to write a paper. We just never have time.
We do have outputs with TE Academy to try to kind of touch upon this. In fact, there's going to be an upcoming course on one AMM mechanism that we're going to kind of put this methodology into play and describe. But more or less what we're trying to do is to bring a let's call it a meta environment where we can actually understand the mathematical relationships that we're seeing exhibited from the system in such a way that we can actually predict what happens when we try to implement such a system. So the idea here is to sort of, and this is kind of a straw man, is to consider a notion in which you were trying to examine the Bitcoin network as a system. You see that it has certain properties like a set of addresses or a set of unspent transactions outputs. This is going to give you a snapshot. You can see it in time. And of course, what you're concerned with is how this thing changes over time. And it's this dynamical aspect of every system that we're concerned with that in a way, in the end, gives this ability of the GDS framework the power to provide mathematical properties that can later on be verified. The challenge here, of course, is that because things change, they don't change necessarily in simple ways. And if you find that you would like to actually change the real world to fit your model, then usually you're in deep trouble. If you're looking and saying, I want things just to be like this way so that I can use a differential equation to update things. If things are more complicated, you would really like a system which will do things that you would like to see. For example, if the set of addresses explodes and adds a new dimension as a new address is added, you want a system that can accommodate that kind of change. If the set of unspent transactions is not fixed in size, but grows or contracts, you want that to be a set that moves in and out and changes over time. And you want to be able to assert properties about that set from the way in which that set is being extrapolated as a system. Now that's complicated, but the idea is to find something that kind of gives you that Occam's razor between being general enough to encompass complex system dynamics and specific enough to uncover those properties that can be formally verified. So you walk along this edge where if you're too general and too abstract, anything can happen in quotes where you don't really get something that you can later on sink your teeth into in an implementation. But if you are too specific, you may throw out, as they say in the parlance, the baby with the bath, that you lose the focus of what it is you're trying to do because you've sort of straitjacketed yourself into a particular paradigm that can only verify certain types of properties. So you need to find this sort of happy harmony in between these two. Now, there is a dynamical systems approach which allows you to do this kind of assessment or analysis just with numbers. And that's a differential equation environment or a difference equation environment where you have a state X, as is described here on the slide, that evolves over time. And that function that is telling you how that evolves over time may itself be changing if that's a function F. And in this case, the state itself is a number or a vector or matrix of numbers that you're trying to get a handle on. This movement in itself then just becomes change of state as vector, the way in which that changes as a set of numbers, new state that comes from that. A generalized dynamical system is very similar, and in fact, it is a superset. It nests that dynamical systems approach. What it does instead is it says the state, the things that can move and can be changed, can be any kind of a data record. And I say any kind, almost any kind. It has to have a little bit of structure to be able to understand how to implement it. But it can be something like numbers, of course. It can be relationships within a database, so a graph or a network. A graph itself could be a state. It can be a set of objects. We were looking at that set of unspent transactions output, for example. That's an object, an abstract subspace that is defined by the architecture of the Bitcoin network. So we look at this as a way of saying, let's lift the problem from the number space into things that are more abstract, that have been guided by this ability to take the system and understand its interfaces and understand how it's actually changing over time by how those interfaces interact with the rest of the system or the boundaries that are there. So the state within the GDS is represented again by X in the slides that are coming. And then we'll have a transition of the state, a mutation of the state, a change that is represented by some kind of relationship, a mapping, not necessarily a strict mathematical function, but a mathematical relationship that can change over time. That actually is in a nutshell is GDS. This is sort of the slide to go back to when you want to get like a handle on what GDS is in its core. So we've got this notion that you can use time as the way of indexing how things are mutating and changing. The nice thing also about GDS is that because it's lifting away from a very regimented point of view in terms of how it's spatially being represented, it also relaxes the temporal aspect as well. It can incorporate things that are happening in continuous time as a differential equation representation would. It can include then discrete time where you have it in fixed intervals that are uniform. Block time, for example, which collect transactions over a series of discrete intervals, and then you get updates every so often at discrete points in time. And most generally though, and this is really, again, nesting, each one of these kind of helps to nest the ones before it, the event sequence time, which gives you an idea of what's happening anytime in a continuous time fashion, but within certain naturally occurring from the data collections or aggregations of time units that you find of interest or that are dictating how the
Yeah.
system.
This is super important actually, because in the world of blockchain, people have a lot of difficulty with dealing with time. And I think it's one of the reasons why dynamical systems thinking has not really made it all the way in, is that this is like hard mode. You can't just think about it usually in, clean discrete time chunks unless you're zooming way out and kind of fuzzing away the details, because even block time is not particularly good representation of time, because you really need to know the exact order in which things happened. And this event sequence time thing basically says, look, if I've modeled my system and I say I only care about these things, this tells me that there's a certain transactions which can be thought of as, touching the states that are in my model that I care about, and I care about exactly what order they happened in. If they happened within the same block, I still care about exactly what order they happened in. If they happen months apart, I still just care about exactly what order they happened in. And I think the difficulty of that is then that you need a slightly more, at least from a dynamical systems perspective, you need to move into the slightly more advanced representations of systems to avoid what is the sort of default representations, which are continuous or discrete. And block time is a kind of discrete time. Windows of clock time are a kind of discrete time. Or continuous time models are good theoretically, but even any computational system effectively has to discretize a continuous time model in order to actually implement it. So, really continuous time is better thought of as, a model of the outside world that you sample from in your discrete time paradigm. So as we kind of contend with time, we really do focus on looking at things in terms of stuff happening in some order. And if you want to think about this as just like lifting data from Ethereum, what you're saying is that the baseline notion of time is the exact order of every transaction. So not just the order of the blocks, but like each block has an order, and then the blocks themselves have an order. So under the hood, there's a massive ordered list. And then what you're doing is just lifting out the ones you care about, letting all of the other ones just not matter, but you still have a strictly ordered list of transactions. And that's the event sequence that you care about. And it can actually happen within a block or across many months, but the notion of time is still relatively well defined. So we do write models or build models in different representations of time, but as long as we're talking about these blockchain systems, I think it's actually really important to kind of think about time as this event sequence thing, and that the event sequence is about the it matters what's in scope, because you don't want to worry about all the events associated with things that aren't touching the states that are in the subsystem that you're reasoning about.
Yeah, I think there's an interesting comment there that it's very dangerous to think of kind of block events as time, even though there's sort of a natural interpretation of blockchains as like a historical record, because at least in like proof of work chains you can get reorgs, and then the past can actually change, which tells you that you really shouldn't rely on on the sequence of events in the blocks as time. You need some separate notion of it. I did want to ask a question from the previous slide. When you say that the state transition is no longer a function, but is a mapping, is that just another way of saying there's some non-determinism of from each state, there's like some number of possible next states?
Right, exactly. We're gonna get right into that, exactly. But that's right.
Okay.
That's exactly the intuition.
I want to respond to the last point though. Yeah. So the other thing is really important, and is that when you don't have finality, when you have reorgs, you need to be aware that there's a sort of, I think of it as a sort of quantum superposition and collapse. Like if you're really doing a near real-time system, you need a much even more complex notion of what's happening. But as you get further into the past, you can sort of rely on the sort of event sequence time inferred from the past blocks and the order within the blocks. But what's interesting about this also is that it's surprisingly unlikely that the reorgs will affect the state changes, because that's the thing that is most likely to how to say, I'm not saying they can't, but what's interesting about this to me is that the graph of dependencies is also pretty sparse. So if you thought of this whole thing as a DAG, and then there's a bunch of equivalent DAGs that have the same state, you can reorganize the order of events such that the state changes don't change, because a lot of the transactions have no dependence. So a lot of the really interesting stuff, and even arguably the MEV stuff, happens at the point where, you know, sandwiches or minor reorgs actually meaningfully affect the financial flows. But, you know, another thing we have to ask ourselves is, what time scale are we reasoning at? Are we digging in and looking at things that are happening at the level of, say, MEV, which is sort of inter-block event order? Are we zooming out? Are we looking at health processes that are defined over days, weeks, months? And, you know, that kind of speaks to the generality of the notion of time in GDS. We don't know a priori which one we're doing, and that when we get into doing a specific project, we use GDS either way, but what we actually end up with in our model might be very different if we're trying to drill down into fine periods of time versus trying to zoom out and looking at long periods of time.
Thanks. So just to give you some ideas of the different pieces of the building blocks of GDS, this is again kind of building out what we would look at as abstractions of what we're seeing inside the systems that we're looking at or under study. This idea of the state is a snapshot of the system at a particular location in time or a particular event, and that it is influenced by other factors. As was just mentioned by Kurt, that this idea that the mapping can change over time is being influenced by other factors. For example, external factors such as exogenous shocks that happen to the system, or internal factors such as participation decision-making that's happening within the system. And once you have that delineation, you can also decide whether or not those are deterministic, that you know what kind of factors are coming in, or non-deterministic, as the word shock is meant to infer this notion that the external factors are things you don't necessarily know, although you may have a data generating process or a random generation distribution that you have as a likely candidate. Now, that's not really the only way in which these things are affected, and sometimes it's not necessarily even the most important way that these types of things are affected. There's also a way in which actions themselves affect the state transitions. And in action, this is where the control theory where it reveals its control theory roots, in a sense, where GDS is coming from. This is a notion of somebody actually making a decision, a system participant coming in and saying, I see the state and I decide something. And we call this decision U sub t in this framework. It doesn't have to be a human or even a person making a decision in clock time. It could be an automatic response based upon certain health metrics, for example, something which has been placed into the system to change the state according to a set of conditions and evaluations of the previous state that it was seeing. But the key thing, and this is the thing I want to try to underscore during the time that we have, is that it's being drawn from an admissible set of possible actions which can change over time. So I'm going to come back to that, and just, but very quickly from a graphical point of view, you could think about it as having a particular state, let's call it xt minus 1, and there's a particular pool of things that an actor or an agent or a decision-making entity can draw from. They draw one of these, u sub t, and then what happens is in the next clock tick, additional actions become available. In this case, it's an inclusive set of actions. So there are some there which were already present before, but now there are some new ones. And so in time period t, there's a new set of admissible actions. And then one of those may be selected, u sub t plus 1. There may also then be an evolution where the things that were valid before are no longer valid. So that you have an exclusive addition of actions, additional actions that are occurring, but those actions now, the ones that are admissible, are the ones that weren't possible before. And then you end up pulling, again, from that set, there may be a decision that is being taken from that individual. We're focusing here not so much on the individual mapping between xt plus 1 in this case and ut plus 2, but on the set u, because in a way what you are looking for is an understanding of the properties such that you allow people to do what they want, or decision makers to take decisions on the basis of what's admissible, without, in a sense, assuming a particular behavior that you wish to actually observe.
So I think, again, like, we're talking about something here where, because in the blockchain context, you are able to explicitly enforce admissible actions. Anything that is inadmissible reverts. So you aren't really designing the behavior of the agents. You're designing the set of actions agents are allowed to take. And by relinquishing any control or any belief of control over the specific actions and focusing on the sets of admissible actions, you get much stronger properties, things that you can actually verify. Now, don't get me wrong, you still care about what choices people take from these sets, but it decomposes the notion of behavior, which is the choice of from the set, and the set, which is the thing that the designers actually get to declare. And so we've made like a lot of our work, literally over years, has been improving our ability to treat these things apart from each other. We treat them both, but to make sure that they're treated differently because they're very different. And I'll let Jamsheed kind of get back into it, but this is probably the single biggest reason why we ended up having to create our own sort of mathematical description, is that borrowing from again, existing engineering fields that are used for, you know, large scale and safety critical systems, like the kind of separation between the deterministic bits, the you know, the state and the state transitions or laws of motion, and sort of inputs that come from an external system, the in this case U, or what we're referring to as G of U, is the canonical decomposition of a control system, of a including like hybrid systems and large scale control systems. And we had to adapt it to account for stuff that happens in blockchains, but ultimately we settled on the GDS framework, which extends well beyond blockchains. And sorry, I'll let you continue, but I feel like a little bit of like, why are we giving you a new thing every time we present this? And I'm trying to kind of justify it at this level of, we needed this equipment in order to separate the way the system acts deterministically in response to an input from the choice amongst the set of allowable things, which is non-deterministic.
Yep. So I won't go through some of the detail, the full details on this slide, just to say that there is a distinction between the set U of T of the admissible actions, and then there's a selection from that, which can be represented perhaps by a mapping G of T, which is often called in control theory a policy, which is also even derived from economic systems as a behavior, where you don't necessarily know what that is, or you can't really infer that or impose that upon individuals.
I think what's tricky about this, though, is that capital U of T is, you know, it's a mapping from the state, right? You're saying the set of things that you're allowed to do is a function of the current state of the system, and it might be local. Like if you're an individual actor, if I want to send some Bitcoin, my Bitcoin address is the actor, and I'm like, well, I can send what I have. I can't send more. Your action set is actually it is a function of the current state of the system. And if I send 3 and I only had 3, I can't send 3 again. If I had 6 and I send 3, then I can send 3 again. But you're seeing the expansion and contraction of the state as a function of the actions taken, but then the change in the set of actions that can be taken as a result of changes in the state. And so very broadly speaking, that's central to not only designing mechanisms, but looking at the way that the interdependence emerges, where different mechanisms mutate the same states and different mechanisms have dependencies on different states. Even like a whitelist is essentially a state for which another method depends. The admissibility of an action could be tied back to your presence on a whitelist. So anyway, this is something that we may end up coming back to. I hope that you guys find useful, but it's definitely been a mainstay in our work over the last few years.
And it is, yes, as Tanner said, it is actually in our paper, The Economic Games as Estimators work, indeed.
So just could I give what I think is a concrete example of time dependence of the set U of T, just to sort of make it concrete and check my understanding. So let's take a model where the state X is like how many Bitcoins you have. And then the actions are like, you either, you send Bitcoins or you receive them. And so maybe at like maybe XT minus 1 is you have like 10 Bitcoins. T minus 1 was, I don't know, you received 1 Bitcoin or something. And then at U of T, the power goes out, and now like sending Bitcoins is no longer something that's in the admissible actions, even though like big So I'm saying big U of t versus big U of t minus 1. The power was on and you could send Bitcoins at U of t. Power goes out and you can't send Bitcoins anymore. Is that the sort of thing we're trying to represent there?
In fact, I'm going to show you a series of slides that does exactly that, but that's correct. So your intuition is spot on. So what happens with these impacts of other factors is that either random or external decisions can come in and change those admissible actions. And these are things that are happening that are coming oftentimes outside of the system, outside of your control, or are realizations of decisions of things that are happening as factors that are not being described by the decision maker at that time. So in that Bitcoin example, that kind of a sudden external event changes the admissible actions. And of course, depending on the kind of realization, you get different changes in the admissible set. And here I've used it as inclusive, but of course, it could easily have just removed the entire admissible action as in the Bitcoin example, that entire ellipse in the center could have just disappeared from one place to the next. And so these other factors have to be included because one of the things you're trying to do is to understand the verifiable properties of the system that come from external factors being of a certain type. And you try to make sure that you understand that external factor system enough, like the relative likelihood of it happening, or if you're going to do a risk analysis, some sort of a value at risk, what is the percentage of time in which I'm going to generate a particular kind of loss given the fact that I'm going to have a particular small amount of this disastrous event happening, a small percentage of the time this is going to occur. These kinds of risk measures are also ways in which you can understand how these external factors enter into the system. To be able to quantify that, you add that then as a particular parameter that affects the state transition. And this is the ZT that comes in. And it's capturing the effects both on the side of the state, which is changing over time, but also on the side of what it is that the individual is selecting, because you can have external factors select changing what the decision makers do. There could be, for example, a system which, well, for example, if you're using Ethereum as collateral and you're actually drawing on that, well, if the price of Ethereum is considered external to your system and it tanks, individual decision-making changes as a result of this. And so this is something coming from the outside of your individual system that affects both the state of the system, perhaps, and how you value collateral, but also affects individual behavior and the description of what it is that they decide to choose. So putting it all together, and again, it's just a slide with a lot of equations, but the nice thing about it is it ties down to a relationship, a particular kind of recurrence relationship between the previous state and the current state. And this is important because that last state there, that state transition map, when you put all of this stuff together and substitute away the functional and the set value dependencies, what you end up with is a way to, if you can observe the state X, a way for the data to tell you what functions of H are consistent with the system that you have just built. And so here's a table, just a quick glance of everything that we've just described very quickly, even some more detail. But it's this idea that that H function, that state transition function, is actually the real data is informing you about that and building for you the consistent universes of the modeling that you could have had, the system properties that are consistent with that value that you get from the data observation. So it ties, even though this is so abstract, it ties directly into the measurement question for data. Sorry.
Yeah, I was going to say the diagram on the right is the one I was referring to earlier,
okay.
where for these diagrams and tables are from the draft of the paper that Jamsheed and I are working on to directly kind of overview this. Some of the notation is like slightly work in progress, but it's the concepts are consistent. We've been using them. We've been trying to make sure that we can describe them. And the trickiest thing here actually, and I think there's a new version of this table, is the dealing with universes, because we have to deal with these like set of all possible actions. The thing that the script U, the set from which the script U belongs to is like, we're still trying to find the right formal representation of that sort of universe. It's not even a set technically. I think it has to be a universe. Yeah, so please like feel free to make comments, but also I think we're iterating on the table from a formalism's perspective, but the concepts are all intact and the relations are well characterized by this diagram on the right, because what we're basically just saying is that we don't know G. So the G operator comes in from outside. The thing that we are actually doing is designing that capital U of X.
This feels like it has echoes of like path integral formalism in physics, where you've got to integrate over like all possible trajectories of the universe or something.
Yeah. Somebody asked where the V is defined. There was a footnote actually for it, but the V we're using it as this, or it's actually there in the input space.
Yeah.
U. Yeah, basically all this is saying is we need to finish this damn paper, because you're right. Like we know that we kind of owe the canonical reference for this as we've kind of kicked it for a few years. I actually shared in the chat too, the first version of what became GDS that I wrote had a paper, I think it came out in 2018, where I just basically did a formalism over Bitcoin and dealt with the expanding state space issue, and basically said, like, I need a model of the state of the system that accounts for, was essentially a vector of balances that grows. And so I can't use a standard control theoretic formalism because I'm blocked by this ever increasing state space of, keys in the address set. And kind of fought with it a little bit and figured out how to squeeze a proof out of it. And anyway, that aside, the formalisms here, I think we're gonna, as we said before, kind of leave the table and the drawing for you guys to use. I personally find it a lot easier to use this than it is to describe this. So when we get into moving forward, I think we're going to try to teach it more by applying it than teach it by like math class, where you're like, oh, here, you need to understand exactly how this works. Actually, at the end of the day, what matters is that you are declaring groups of operators. Like if you say or really not operators, but you're declaring F, X, and the map from X to U. So essentially the mapping from the state to the set of admissible actions, the capital U, and the mechanism F, which is the thing that takes a current state and an action, and then the state space itself, this sort of domain X, this script X. If you have a data structure that represents the script X and a set of admissible messages or inputs as a function of X, then you can actually create a what is effectively a differential inclusion, or it's a discrete time differential inclusion. But this is super important because what it means is that given a current set of states and a current set of actions that can be taken from those set of states, you can get the new set of states from which you can get the new set of actions. And what this means is that there's hiding behind this a subspace or subset of X, which is reachable. In fact, you can even get fixed points in the reachable space, which means that there's like a weird non-trivial differential topology to the space that your system can achieve. And what you start to do is recognize what parts of that state are totally unreachable, and thus you can kind of treat them as, you don't even have to worry about behavior because the no behavior can get you there. But then you have other things that you could view as risky in the sense that there's an open edge somewhere and you're like, oh, well, we now know which kinds of sequences of behaviors might actually take us to that edge and what states that passes through. And that actually ties back into our discussion of risk modeling. So if you understand the shape of space, you can start to understand what points are on the path to the danger zone and start to understand whether you're on that path or not, or how to secure or prevent you from proceeding on that path. And that's when you start to reason more about behavior and incentives, because you're not trying to stop people from doing things. You're just trying to shore up the boundaries to the unsafe regions.